The other one is acidic. The two on the right. That's why they are called aspartic acid and glutamic acid. Okay? Acidic amino acids have a negative charge. Basic amino acids have a positive charge. Some of you may be wondering, how did they gain these charges or positive or negative charge? Did Miss O is your chem teacher? No, who's your chem teacher? Miss O. Miss O told you about acids and bases yet? Have or don't have? Okay, wait, this half have, then half don't have. Oh, don't have. Okay. I think she'll teach soon because some other classes are learning it already. Acids can release H plus ions. It's just FYI, okay? For biology. For chemistry, Miss O will go more in depth. Okay, just for your information if you are curious. For example, if you look at acidic amino acids, you see a COO minus. Right, you see a COO minus, you can highlight that. If you are curious how that appeared, okay, it used to be this. It used to be a COOH, but then after it lost one H plus, it then became COO minus. So that's how it works, for your information. Okay? Okay, then what about the basic ones? They are positive because they can, rather than release, they can receive. So now I spell receive. It's the I in front or behind? Correct, okay. Receive H plus ions. So if you look at, for example, let's look at lysine. If you look at lysine, you see it's an NH3 plus. You can highlight lysine, the NH3 plus. How did that occur? Well, it used to be an NH2, but after it gained one H plus ion, it then became NH3 plus. Okay, this is all FYI. Okay, let me box up the FYI parts. Just so that you can appreciate this a bit better. Okay, that's the first category of amino acids. Okay, I'll take a pause first. Then we have two more categories. Then we are done with the recap for amino acids. Okay, I see what you stop right there. The second category of amino acids are they put hydrophilic polar ones. Polar amino acids. Okay, how do we tell something is polar? Usually if you see a OH group, then it's going to be polar. Okay, usually we see OH group. Other signs that may be polar, maybe you will see a C double bonded to O. Okay, or if you see a NH2, these are signs that they are polar. Hey, Shermaine is here. Hey, Henry, sorry, I forgot to ask, do you record now?
Yeah.
You got press up?
Oh.
Oh, okay. Are you press up? Thank you. Okay, last one. 3. Last category are non-polar. Non-polar amino acids. How do you tell something is non-polar? If you see a lot of carbon bonded to hydrogen, that is a sign that it's usually non-polar. Lots of carbon bonded to hydrogen. Okay, 3 broad categories. For those that are done, can you tell me category 1, 2, 3? Which one is hydrophilic, meaning they love water? Which one is hydrophobic, meaning they hate water? Okay, this is a practice. We are applying things from chapter 1. Can you tell? Charged, polar, non-polar. Which of these 3 will love water? Okay, a quick discussion. Must try, this one must try. I'll tell you the good news. We don't expect you to memorize the 20 amino acids. But we may provide you one amino acid that asks you, is this hydrophilic or is it hydrophobic? Okay, this is the skill you need to apply. But I don't need you to memorize amino acids. Okay? I tell the truth, I also don't know how to draw all the amino acids. Okay, ready? Okay. Who says group 1 loves water, hydrophilic? No? Who says group 2 loves water? Okay. How we tell? Because they are polar, right? They will have partial charges. So if I join partial charges, this one will be partially negative, partially positive, can track the water to itself. Same here, the nitrogen will be partially negative, hydrogen partially positive, carbon partially positive, partially negative. Can track water to itself. Okay. Alright, what about this? Is this going to be hydrophilic? Okay, so hydrophobic. Okay, so let's write this additional details down. Polar groups will be hydrophilic. They love water. Non-polar will be hydrophobic. We do not like water. What about charged R groups? They like water, not like water. Let me take one example. Let's look at glutamic acid. Okay, let's look at the R group of glutamic acid. Glutamic acid. Okay, I'm just going to draw the R group, which goes like this: CH2, CH2, COO minus. Okay, minus over here. Would this love water? Which is possible. Do you remember in chapter 1, I asked you to do something like we drew sodium ion. Then I asked you what will happen if I have water nearby. And the water molecules will do something like that. All the oxygen will be attracted to the positive part. Remember? I hope this configuration makes sense to you. Now, remember all the oxygen is partially negative. And all the hydrogens are partially positive. Okay. So think of it this way. Something that's fully charged is like a very strong magnet. Something that's partially charged is just a weaker magnet. But if I put two magnets together, can they attract each other? So you can. Okay? Because one is partially charged, one is fully charged, can still attract each other. Okay? So, can the R group of charged R groups attract water? Also can. Right? How will I draw this instead? The hydrogens will be the ones that will be very close to the negative charge. Yeah, the water molecules. So if you like to, you can indicate to yourself that this is something that a lot of people don't notice, that charged R groups are hydrophilic. They also love water. In fact, they really love water. If I have to compare who loves water more, number 1 loves water more than number 2. Okay? Because one is like a strong magnet, the other one is a weaker magnet. Okay? I say again, charged R groups love water a lot more than polar R groups. They're much more attractive. Okay, so maybe you want to write this down. If you want to make it a little bit more clear to you, you could draw a water molecule being attracted to a particular R group. Okay? Now I'll take a pause for any questions from the floor. But then we have just done a recap of types of amino acids. Yes? Yes? Sir? No. Who do you normally sit beside? Okay, off. Yes? Okay, so there are 3 special cases. May I get you to shift the special case to hydrophobic if you have not done so? Yeah, last week I asked you all to like shift them down. Okay, if you have not, just shift them down. Or you can just create one bowl box around all of them. Okay, they are hydrophobic. Okay, so for your quiz, there will be after the March holidays. Don't memorize this. Okay? I have some very hardworking students that go and memorize all 20, know how to draw every single one, know how to identify. Only just be able to tell me if it has these characteristics. practice. Without looking at your textbook, I'm going to draw one R group of amino acid. You tell me whether it is category 1, category 2, or 3. Ready? Okay, this is the only skill to pick up, right? So don't you feel intimidated about drawing or recognize or knowing every single amino acid. Okay, I'm going to draw. C. Which category? 1, 2, or 3? Okay. Is this particular R group charged, polar, non-polar? Okay, I know it's early morning, but I don't want to talk to a wall. Okay, so we all verbalize, practice the vocab. Okay, so is it polar, non-polar, or charged? Okay, just shout out your answer. Polar? Okay, let me rephrase the question. I can have two kinds of questions for this. Next, is this R group hydrophobic or hydrophilic? Yeah? Okay, hey, practice the words. I say again, is this R group hydrophobic or hydrophilic? Okay, who says it's hydrophobic? Raise your hands. Who says it's hydrophilic? Okay, how do you tell it's hydrophilic? Okay, you can see the OH over here. Yeah? Yeah? OH is polar. Ready? Okay, we test one more time. So ready, the skill is to be able to tell me if it's polar, non-polar, hydrophobic, hydrophilic, or charged. That's all. Okay? Okay, we try one more. Okay, so let me look at amino acids. Okay, ready? Okay, this particular R group. Okay. Some of you maybe cannot recognize the amino acids. Let me draw on top over here. C, okay, this is the typical amino acid. Okay, so it's the thing below that's being replaced, right? Okay, so let me choose one particular amino acid. Okay, so prepare my question. My question is this R group hydrophobic or hydrophilic? Can? Yeah. So is it hydrophilic? Yeah, it is, right? Okay, so we just practice Really, that's all I can ask you. Okay, I'm not going to ask you to draw the amino acids. Let's try another one. Next amino acid. Don't look at the screen. Just practice the skill. Okay. Is this R group? Ready? Is this R group hydrophobic or hydrophilic? Philic? How do we tell? Right, okay, see? This over here, this over here. Okay? Okay. So one last one. Is this R group hydrophobic or hydrophilic? Hello, okay. Is this R group hydrophilic or hydrophobic? Okay. How do you tell is hydrophobic? Largely CH. Can you see that? Okay, so I just want to reassure you, this is the skill you need to have. Not to memorize all amino acids, just to be able to categorize. Yeah? And then normally, okay, I tell you up front, you put it in an MCQ question. We will have the MCQ, we will put down maybe 4 amino acids there, and then we will put down 4 options. And then we will put hydrophobic, hydrophilic, polar, non-polar, and then you just need to be able to tell me what's one. Okay? Yeah? Okay, so let's recap on the first part. The next part of our lesson, we learn how to form peptide bonds. Remember? Yeah, we form a peptide bond, and we also learn where we can break peptide bonds. And then we went into our bead activity. In our bead activity, I asked all of you to form beads of amino acids, right? A chain of amino acids that form a polypeptide. Are you all still talking? Okay, I'm going to erase the whiteboard now. going to erase up. Okay, so that was about amino acids. Okay, but the beauty about having so many amino acids is that, hey, that means we can have different combinations of amino acids, right? And that plays into our bead activity. Because these combinations of 20 amino acids, right, I can play around with 3 variables. Number one, I can play around with the type of amino acids I use, the number of amino acids I use, and the sequence of these amino acids I use to form different, what we call primary structures. Primary structures are nothing more than variations of number, type, and sequence of amino acids. So last week I gave an example. I drew on the whiteboard different primary sequences. So for example, this could be sequence number 1. Circle, diamond, square, square, circle. Each shape representing amino acid. I could have structure number 2, where I change instead the type of amino acids that are present. Now no longer exactly the same sequence as the top. I change the type. I can also change instead the number of amino acids. So rather than 1, 2, 3, 4, 5, I could have 1, 2, 3, 4, 5, 6 amino acids. That's a different primary structure altogether. I can also change the sequence of things. Perhaps rather than starting with a circle, I start with a diamond, then followed by a square, then a circle, then a square, then a circle again. Yeah? Primary structures are nothing more than different variations of types, number, and sequence of amino acids. Okay? So that's what a primary structure is. How many primary structures are there in our body? Well, a lot. Lots and lots of different primary structure. One primary structure could result in an enzyme in your stomach. One primary structure could be the protein in your hair. Another primary structure could be another enzyme, but maybe in your small intestine, and so on and so forth. Every primary structure would eventually result in a function. Okay, that was one part of our lesson. And then this is where we left off. We left off with this idea that that when we take these primary structures, okay, if we take a primary structure and we let it fold, right, if it goes through this process of folding, then we achieve something, the next level of structure, which is a tertiary structure. Okay, I'm going to press play. Watch as this primary structure folds. Okay. The next level of structure that we learned last week was this level of structure. Okay, when primary structures fold, we achieve the next level of structure called a tertiary structure. A tertiary structure is nothing more than a highly folded polypeptide. Okay? But what are the features of a tertiary structure? Okay, it is highly folded. It has a 3D globular shape. Globular means like a random turn, like a ball shape. Okay, globular. You know, sometimes you take your nose, what comes out is globular shape. What else would be globular? Okay, and that's a tertiary structure. Notice I've skipped one layer of structure. For those that are following the notes, if you look on this page, actually we skipped the layer, the level of structure in the middle. This one over here, we skipped it. We went straight to here. Okay, last but not least, we learned a few things when we did our activity last week. We learned that the tertiary structure, how a polypeptide folds, depends actually on two things. Number one, it depends on what kind of medium I place it in, right? If I place it in water, it will fold this way, where all the hydrophobic will cluster together in a core. But what if I swap it to oil? If I change it to oil, you'll find that instead, all the hydrophilic ones will end up clustering in the middle, and the hydrophobic ones on the outside. Right, so how a tertiary structure folds is determined by number one, the medium it is placed in. That's the first thing we learned last week, and I saw all of you all folding your structures differently. There's one more factor that affects how a protein folds. This one is, you can see clearest when I instead put it in vacuum. Okay? No medium at all. No water, no oil, but it can still fold. Okay? Okay, I'm going to press play. Watch as this polypeptide folds into a protein, even without being placed in water or oil. Okay? They are still coming together. It is as though there is some sort of interaction or bond between the amino acids by themselves. Okay? So the second factor that affects folding is the bonds or interactions between amino acid R groups. Okay, the second thing. Can you list down some bonds or interactions that can help hold the R groups together? What do you think is attracting all these R groups together? Okay, here's some bonds. Number one, hydrogen bonds. Hydrogen bonds will be attracting all the green ones, the hydrophilic ones. Yeah, the hydrophilic R groups will be attracted to each other by hydrogen bonding. You notice the blue and red ones, the positively charged and negatively charged ones attracted to each other? Yeah, those are ionic bonds. You notice the yellow ones clustering together? Okay, those are hydrophobic interactions. Last but not least, you see these two amino acids, cysteine and cysteine. There's a yellow bond over here. A yellow bond is what we call a disulfide linkage. Okay, in total there's 1, 2, 3, 4 kinds of bonds that can hold R groups together. Yes, Shamim. Oh, where are covalent bonds, is it?
Yeah, they're like possible.
It's possible. Okay, so if I want to be specific, this disulfide linkage, you see the yellow bond over here. I don't know if you can see, let me zoom in. Can you see between cysteine? There's this yellow bond over here. That's a covalent bond. Okay? So disulfide linkage is a type of covalent bond. Okay, I'm going to walk around. Some of you are very shy. If you have any questions, please ask me and catch me when I walk past. Oh, let's check with my reason. What is this thing just floating right there? if I put in water, oil, you won't do this. It's going here and there everywhere. Okay, if you think you are okay, then we will go to CA 1.5B. Okay, I'll come back to this tomorrow for our last lesson. Can I go to CA 1.5C? Yes. Their percent interactions. So I put bonds / interactions. Okay, may I invite you to go to 1.5C? Let's skip A. Let's skip activity A. I'd like you to go straight to activity B. Okay, we're going to learn one more level of structure. We skip from primary to tertiary. There's one more level of structure in between. Okay, I'd like you to scan this QR code and explore the virtual model that I provided to you. Okay, if you scan the QR code, this is what you should see. You should see an enzyme that you're familiar with that is swirling in your mouth right now. It's your salivary amylase. Now I'd like you to click on the QR code or open the link and go to this model. I'd like you to explore the model this morning. So one simple activity for this morning. As you explore the model, I'd like you to explore different ways of seeing this model. You see at the very top, you see protein display options. Okay, then there's ball and stick, wireframe, trace, cartoon, space fill. I'd like you to try and click on all of them to see what a protein can look like in various different forms. It's just various ways of showing a protein. Your first activity in your pairs is to find patterns in the way the protein folds. I say again, I'd like you to find patterns in the way the protein folds. Do you see any similarity in the way it folds here and there? Once you found some patterns in the way the protein folds, I'd like you to zoom in and screenshot these patterns. This is a highly folded protein. Wow, it folds in many ways. But if you zoom in, you can spot some patterns in the way it folds. I'd like you to take photo of these patterns. Can you see any patterns? You need very sharp eyes to spot the patterns in the way the protein folds. Some areas they don't fold randomly. They fold in quite a repeated way. I don't know how many of you can spot the patterns. If you think you spot the patterns, please screenshot and put it into the next stage of your class activity. Then we're going to discuss what patterns can you see. If you are still at ball and stick or wireframe, may I invite you to choose the trace option. Okay, can you choose trace option? Trace option just shows a simplified version of the folding. Can you see any patterns in the way the polypeptide folds? Some parts fold in very similar ways. Can you spot it? Use your eagle eyes. If you still cannot spot it, you can click on cartoon. That's another way we can show polypeptides. Can you see the patterns now? Once you think you found any patterns in folding, I'd like you to screenshot and put inside your class activity. red thing is a single, it's like a, it emulates like this one. Such, that one. Okay. Do you see any patterns in the way the wire of the polypeptide then folds? Do you see? Are there certain ways it folds and it repeats itself here and there? Okay, you see one pattern in the way it folds? Oh, too much. Yeah, the name we figure out later. So we just spot the patterns first. You can toggle between trees. Can you see the pattern? What are the patterns? So there's one pattern, then it goes this way, right? See another pattern. Okay, to truly see the patterns, you need to toggle between trace and cartoon, trace and cartoon, trace and cartoon. Then you can see the patterns more clearly. Yes. Okay, so the red one, right, it emulates digest starch. So they are showing you a settlement of the starch. The green, if I'm not wrong, they are ions that are required that emulates water. Shreya, you spotted any patterns? Okay. That's it? Okay. I'd like you to look carefully. There's one more pattern in which the proteins polypeptide folds. What about both of you? Spotted any patterns? Coils, right? You notice that you see the coils here and there everywhere, right? You also spotted coils. There's one more pattern in which the polypeptide folds. This one, the second one is very hard to find. Henry, do you spot patterns? Any more? Okay, I'd like you to look carefully. Look carefully. Any other way in which the polypeptide folds? Okay, a lot of you can find one pattern, which is the curly-whirly pattern, right? You saw that? Now the polypeptides seem to like to curl themselves in a helix. Okay, the challenge is finding the second kind of pattern. I'm going to zoom in to one of the patterns that all of you found. Okay, wow. Okay, a lot of us found this curly pattern, right? In a way, the polypeptide can fold. Did anyone manage to find a second pattern? The second pattern is the other one to spot. Okay, you think you found a second pattern? Can you raise your hand? You think you found a second pattern? Can I see? You lost it yourself? Ah, okay. How would you describe this, the way this folds? You said that the other one is like curls, right? So how would you describe this one? Sorry? Oh, like a zigzag pattern. So you see the curves, right? The curves are something you can see here, there, everywhere, right? So do you see any other pattern? screenshot some patterns here? Okay, now I'm going to review the patterns to you. If you go to class activity, you scroll, okay, you should put your photos in here. Then you go to step C. Can you click on cartoon format colored by structure? Cartoon format colored by structure. Okay, it's under the thing called secondary structure. If you click on that, you will see this. Pink and yellow. We have color coded one pattern in pink and one pattern of folding in yellow. I believe a lot of us spotted the pattern in pink, right? We saw the curly ones, right? But do you see the one in yellow? Let's look at the one in yellow. What is distinctive about this particular pattern? Oops. If you toggle between cartoon and trace right now, okay, watch what happens. I'm going to go trace, cartoon, trace, cartoon. Okay, go back and forth. Then you can appreciate it a bit better. Let me look at the trace version. Notice that the second kind of pattern in which polypeptides can fold is this. Okay, this is the first one. Polypeptides can fold in like a helix, right? The second pattern you notice, look at the yellow ones. If I up it from certain perspective, right, it looks like, let's zoom into this part over here. You know what? It looks like sheets. They're kind of like parallel to each other. And from certain perspectives, if I were to take this sheet and look from certain perspective, it looks like a flat sheet. Yeah? So there are two kinds of patterns that we can observe over here. One is a helix pattern and one is a sheet kind of pattern. Okay, so let me overlay this. There's a name to these patterns. This is called an alpha helix. I tell you, this chapter got a lot of alphas. Then this one is called a beta pleated sheet. They say it's pleated because when you actually I don't pleat girls' hair, but this looks like a pleat. Does it? No, not really. Okay, imagine your hair when you need to pleat it in a certain way. So I think that's why it's called beta pleated sheet. Okay. So may I invite you now? Go back to your screenshots and can you label all the alpha helix patterns that you see and all the beta pleated sheet patterns that you can see. You can use this particular model to help you find all the patterns. You can use trace or cartoon, up to you how you want to show it. So could you screenshot the two patterns so that you have an idea of what to look out for? The skill to pick up here is, one day I will show you a protein. Then I'll ask you, can you spot any patterns? Then really the skill is to tell me, oh, I see an alpha helix, or I see beta pleated sheets. In fact, if you want to test yourself, you scroll all the way up to this class activity. I provided a protein over here. You tell me, what kind of pattern do you see? Really, that's all the skill I need to pick up. Okay, for those that are done, screenshotting and labeling, you go back to the first activity over here. Look at this protein. Can you label all the patterns that you observe? I hope it's obvious, huh? I hope it's obvious. This particular pattern you see on the screen. Okay. So we know that there are primary structures and there are tertiary structures. This is the gap we're going to fill in. We call these two structures secondary structures. What are the characteristics? There are only two kinds of secondary structures: alpha helix or beta beta sheets. Unlike a tertiary structure is large-scale foldings. Secondary structure is what I would describe it as that is localized folds. Localized means you see this helix, it's not throughout the entire structure. It's like you find one here, you find another one at another location, you find one at another location. It's very localized. It's not spread out across the entire one. Okay, so that's what I mean. Secondary structures are localized folds. You can find two kinds of localized folds: alpha helix or beta beta sheets. Yes. Yeah. Okay, for those that are done, here's a brain. Yes. Okay, so Shreya asked, can you find alpha helix and beta beta sheets in all proteins? No. Okay, let's try another protein then. Okay, I'd like you now to go to Google. Let's search for protein. Insulin protein structure. You click image. You can find insulin protein structure over here. If you look at this structure, you tell me what kind of secondary structures do you observe here? Do you observe alpha helix or do you observe beta beta sheet? You see all the different colors, right? Actually, we only observe helixes, right? So not all proteins come with both kinds of secondary structures. Some only have one kind, some have both. It really depends. So that's why the skill to pick up here is to be able to have sharp eyes to spot the patterns, not so much to remember or memorize. If you want to practice, you can really go into Google and type any protein you want to find. Okay. We know amylase, right? Let's look at what other digestive enzyme you know of. Amylase, show me one. Sorry? Oh, aminopectin is starch. Yeah. Hydrochloric acid is not enzyme. That's a chemical. Okay, any other enzymes you know? Protease. Okay, let's try a protease. One example of a protease is trypsin, right? Okay, ready? So let's type trypsin. Then let's look at the structure here. What kind of secondary structures do you observe here? Okay, so this is a skill to pick up. What kind of secondary structures do you see here? Can you discuss with your partner now? Okay, see if you can practice and see if your eyes are sharp. What kind of secondary structures do you observe? Ready? Who spotted one secondary structure? Who spotted two secondary structures? So, can see or not, right? Sharp eyes. I will not provide you color, so usually what we will provide you is black and white. But you should still be able to see the structures. You see, over here is a helix. Can you see the beta sheet? Where is it? Oh my god. Okay. You saw the arrow. Usually beta sheets have arrows. What they are telling you is that it's going in this direction, and this direction, this and this and this. That's what the arrows represent. Okay, just showing the directionality. It's not a skill to pick up, it's really to spot these patterns. Okay, I'm going to end off today's lesson because I think we learned a lot today. But I want you to ask yourself this question. Can a protein have all three structures at once? Primary, secondary, and tertiary. Can I ask this question again? Can a protein have primary, secondary, and tertiary structures all at one go? Okay, please discuss. This is really a brain teaser. So my question was, can a protein have all levels of structure at once? Okay? You ready? Yes, Henry?
I thought all proteins have primary structure.
Oh, okay, Henry just that was a very weird question. Then his reply is, don't all proteins have primary structures? They do, right? You cannot escape it. Every protein has a unique number, type, and sequence of amino acids. So yes, number one, all proteins have primary structures. They cannot be escaped. Do all proteins have secondary structures? Okay, I would say I've scoured the internet to try to find a protein without this kind of helix or beta sheet. I actually cannot find it. Okay, so I'm going to put a most. I'm going to say most. Most proteins have secondary structures. I honestly don't know if there's one that doesn't have. Just cannot find. Now the question is, do all proteins have tertiary structures? Do all of them fold large scale? Okay, yes. Right, I'm going to show you right now a protein that has primary and secondary structure but does not have a tertiary structure. Ready? And that protein is called, all of us have this protein, it's called glucagon. Yeah? This is a protein with only a primary and secondary structure. You don't see any large scale folds here and there. Yeah? By the way, this protein is running through our body right now. It helps regulate our sugar levels. It's called glucagon. It regulates the amount of glucose in our body. Okay, so some of us, some students usually have trouble understanding the three layers of structure. Let me show you. If a protein only has a primary structure, it will look like this. Just like a straight line of beads. Nothing more. Okay, lots of amino acids. If it has a secondary structure, it will look like this. Rather than just a straight line, it would have maybe one localized alpha helix, maybe one localized beta sheet. If I take this and make it have a tertiary structure, this is what it will look like. Rather than just a long straight line with localized folds, let me bend these parts. Let me instead now alpha helix, then we fold a large scale fold, beta sheet. Okay, so a tertiary structure must have this kind of large scale folds. Okay, This is an example of a protein that does not have any large scale folds. It only has small scale folds. Yes. So, a question. Do secondary structures and tertiary structures, can they exist at the same time? Can. So you look at this particular protein over here. I observe that there are localized folds, which are called secondary structures. I also observe that there's this large fold over here, this large band. So I observe that there's a tertiary structure also. So yes, a protein can have all three levels at once. Yes, Shameen? Tertiary structures made of secondary structures. Okay, let me show you a tertiary structure without any secondary structures. Okay, it will simply look like this. Lots of large-scale foldings without any local fold patterns. Okay, so if a protein only has large-scale foldings, then it only has tertiary structure. Let me show you this, but with some secondary structures in between. If this protein were to have secondary structures, it will look like that. Maybe at this region over here, there's one alpha helix. Maybe at this region over here, there's another alpha helix. Maybe over here, I have one beta hidden sheet. Okay, a tertiary structure simply refers to large-scale foldings that brings everything into one block. Okay, so Shameen, to answer your question, I wouldn't say tertiary structures are made out of secondary structures, because I could have just a tertiary structure without any local folds here and there. It takes some time to, yes, Shameen still up. Sorry? Oh, okay, good. So this in between lines, like this region over here, where it's folding, right? Shami, you're asking? Yeah. What kind of structure is it? This is just a primary structure, lor. Yeah, that's just a primary structure. It's just amino acids. Yeah. But if you look at this as a whole, there's a lot of large scale folds. Then we will consider that this protein as a tertiary structure. To practice, normally what we can do is that you can just Google a random protein, then you test yourself. I'm going to Google a protein that you know of. It's called hemoglobin. You know hemoglobin? It's the thing that goes through your blood. It's in your red blood cells. Hemoglobin protein structure. Oh my. I want a spinny one. Yes. I gym. Okay? When you look at this, can you tell me how many levels of structures do you observe? Sorry, my question is how many levels? So, remember Henry said all proteins have primary. So we clear that. Next, are there secondary structures? Have. Okay, so we clear that too. This protein has so far 2 levels of structure. Does it have a tertiary structure? It does. Notice that it is highly folded. Everything is brought together in one lump. Okay? So another clue that something has a tertiary structure other than large scale folding, it is often globular. Globular means it is one lump. If there's no large scale folding, it won't be a lump. It will be just like our simulation. This simulation over here, it will just be spread out like that. This has no tertiary structure. But if I let this play out and come together, now it comes into one lump. That's a tertiary structure. But does this have secondary structure? Actually, we cannot see any. Okay? Okay, so that was a lot to take in. We'll now end off today. You can touch up your notes. Okay, but today we mainly learn a new level of structure, which is the secondary structure. They are nothing more than local patterns of folds. I would say most proteins have all three levels. Yeah? I could only find that one funny protein, glucagon, that only goes up to level 2.